So this chapter is going to be about the association between two variables, scatter plots, if you will. And there are some things that you already know about scatter plots and you'll be really comfortable with probably most of what we do today. And eventually we're going to move into stuff that you've never really talked about or seen before. So why do we study the relationships between variables, and how is this chapter different than the very first section of chapter 1, where we also studied relationship between two variables? Okay, here's why we study relationships. It helps us make predictions or explain outcomes. To help make predictions or explain outcomes. So that we can take a small amount of data, a sample if you will, and we can possibly make predictions about the outcome. The difference between this chapter and, you may not remember 1.1, but it's where we talked about like two-way tables and bar charts, pie charts. Those were relationships between two categorical variables, categories, and this chapter is about relationships between two quantitative or numeric variables. 1.1 was about, and you can shorten this whatever you need to write, 1.1 was about relationship between two categorical variables. Really, two-way tables are the way we display that. Segmented bar charts, mosaic plots, and chapter 3 is about relationship between two quantitative variables. Before we start looking at scatter plots, and you might need to create one, you need to know the difference between explanatory and response variable. And I'm not sure, have we touched on that in this class yet, or was that my on-level stats class? Have we talked about explanatory versus response yet? Okay, well, response variable is just going to measure the outcome. It's kind of what we want to know about, what we'll make predictions about most of the time. It measures the outcome. It's going to be on the y-axis, and it's what we want to predict. What we predict. Whereas the explanatory variable helps predict or explain changes in the response variable. It helps predict or explain, hence explanatory, changes in the response variable. And that's going to go on your x-axis when you sketch it out. Now, in some cases, if you're trying to make a scatter plot, you're trying to decide which one might help predict the other one, which one's the outcome, what comes first, what comes last. Every now and then, there might be two variables that don't really seem related. There's not a clear explanatory versus response relationship, so just make a little note because I don't want that to drive you crazy. In some cases, there isn't a clear explanatory response relationship. An example of that would be like SAT math scores versus verbal scores. One of those doesn't help predict the other one. One of them doesn't help explain the other one. But you might plot those against each other on a scatter plot. So every now and then, if you're trying to figure it out, there may not be a relationship there that's clear. I think I've already addressed how you know which variable to put on which axis, but where do you start each axis? So if on this test, or this chapter, if I have you build a scatter plot, I'm going to make sure that you put the explanatory and response variables on the correct axis. And then I'm going to make sure you scale everything appropriately. And so you don't necessarily have to start at 0, 0. You want to start and end each scale to minimize blank space. You don't want to create a bunch of gap when you're building a scatter plot. So start and end each scale to minimize blank space. And what I really want to emphasize, because I saw this issue with the histogram on the chapter 1 test, is be consistent in your scale. So if you want to start with 0 and then the next number is 50, that means you are now counting by 50s. You can't just jump to something different. You can't go from 0 to 50 and then 55, 60, 65, 70. Just as an example, be consistent in your scale. When they're grading your scatter plots on the AP exam, the easiest way to lose points is, there's a little cartoon for you, label your axes. Label, put your units, get all those points that you can. I'm going to play a little AP Daily video for you, and he's going to answer this question: what 4 characteristics should you consider when describing a scatter plot? So we used the SOX acronym to describe distributions. There's another acronym. He does it out of order than the way I'm going to teach it to you. But you don't need to write anything here. We are going to write this together as a class because I'm going to teach you the acronym and we'll go in a slightly different order. But I do want you to just watch his explanation. And this is video 2.4.2. Okay. We're going to do 3 of them right here, and then when we turn the page, we'll be able to fit the last one on there, so I left extra space here. And the acronym is DUFS, D-U-F-S, and that will just help you remember. The first thing that I want you to describe would be direction. Your options there are positive, negative, or none. If you want to quickly sketch out, remember we're fitting 3. We're fitting the direction, unusual features, and form on the front here. So draw these kind of small. You might have a positive direction. That doesn't necessarily mean it's linear, but as X increases, so does Y. You might see a negative direction. Again, that's as X increases. Notice X is always increasing, but in this case, Y decreases. That would be negative association. And then no association would just be complete randomness and scatter. We can't really tell what direction the association is. So that's the D in DUFS. Tell me the direction. Unusual features. Points outside the overall pattern. Like that person with really low attendance rate in the video. Or you might see clusters. So again, draw this kind of small. When I say points outside the overall pattern, you might be thinking outlier. That's one type of point outside the pattern. There are also going to be some points we talk about later in the chapter called leverage points that fall within the pattern, but they're still unusual, so you would want to mention those leverage points. You don't really know what that is yet, but we'll learn about it. So I'm just going to draw like kind of a strong positive relationship, and then in a different color I'm just going to put a couple of outliers. If you see anything like that, then describe those possible outliers. Clusters, I'm going to zoom in as I draw this because it is so tiny. So clusters can kind of happen. You might still see a positive relationship, but like a couple of clusters of dots. And then I really want to mention this because I don't want it to be something I don't mention and it shows up on the AP exam. This is really weird, but you could have clusters that have positive relationships within the cluster, but the overall pattern of the entire scatter plot is still negative. So that's kind of a weirdo one. Clusters will be pretty obvious. If you can fit it on there, strength. Actually, hang on. F is form. Form. It's going to be linear or non-linear. Those are your only two options, okay? Linear. Non-linear might show some kind of curve. But you would just simply say linear or non-linear. And then when you turn the page, so that's DUF, the S is going to be strength. Strength. And you could possibly describe all four of these characteristics in one sentence on a free response. So for strength, what that means is how closely the points follow the form. So everything I'm describing, you could also talk about in a curved pattern. You could tell me that a curved pattern has a really strong relationship. Okay, it doesn't have to be linear, but strength is how closely points follow the form. And so for this picture right here, that's linear, it's positive, and it's strong. Because they all closely fall into the form of being linear. Positive, linear. This could be non-linear, but still really strong. Positive on that one as well. Non-linear. Weakness is going to be when you can see some kind of association, like, you know, as X increases, so does Y. So I can tell that it's positive. I can tell there's no curve to that pattern, but it's going to be on the weak side. Because the points aren't very close to the form. This would still be positive and linear. There's something that will help us measure strength and direction, and it's called the correlation, and the variable that we use for that is R. And so it says, what is it? Well, it helps describe scatter plots. For linear associations, correlation measures strength and direction. R will tell you about strength and direction, but it will not tell you about form. Just because you see R, that does not mean there is a linear association. So even in this example that I drew right here that has curvature to it, that's nonlinear, this has strength. It does have a correlation, okay, and it does have an R value that will show strength. So R does not mean necessarily that we're talking about a linear pattern, so just keep that in mind. And here are some examples of R so that you can see. In this first scatter plot, and the axes aren't labeled, there's no numeric value, but the pattern here is it's pretty scattered. And I want you to notice the correlation is 0. On the next scatter plot, I noticed that it's got this downward trend. So R addresses that with the negative value. 0.3, I'm not really going to say anything about that right now. When R is positive at 0.5, it looks kind of like this. So the dots are kind of starting to get a little bit closer together towards the form. We've got another negative one. As X increases, Y decreases. 0.7 now, the dots are getting closer together, kind of bouncing forth between positive and negative so that you can see a bunch of different ones. 0.9 looks like it's getting stronger. And then on the very last one is negative 0.99, and that shows a lot of strength right there. One way that you can kind of measure strength for yourself is draw an oval or a circle around the dots. Let me show you what I mean. So this one would almost be a circle because it's so scattered. Whereas on the next one I could draw an oval, still kind of fat, but I can draw it slanted to show my negative association. This one would be a little bit skinnier of an oval in the positive direction. So as we get skinnier and skinnier, we're showing more strength. Which leads me into the next part. What are some characteristics of R? R is always going to be between two numbers. And those two numbers are -1 and +1. If R is negative, that means less than 0. If R is negative, that means there's a negative association. Negative association. And R being positive is a positive association. And that's kind of a common sense deal. If you see a negative sign, it's a negative association. If you don't, then it's positive. The closer R is to 0, the weaker the strength. Like, look, when R is 0, it's like you can't even tell what form that has. And then as we move from left to right in these examples that are pictured here, you can tell the 0.3, 0.5, 0.7, 0.9, 0.99 gets stronger and stronger and stronger. So as R gets closer to 0, R close to 0 means weak. The closer R gets to -1, then it's getting stronger in the negative direction, and the closer R gets to +1, it's getting really strong in the positive direction. So let's just sum that up by saying R close to positive or -1 means strong. So R addresses direction and strength, but it doesn't necessarily mean that you are dealing with a linear association. Does correlation imply causation? Not necessarily. You could have confounding variables. Let me show you. I'm going to play another quick little video, and I'm only going to play part of it that's in the middle here. So bear with me. At the bottom of that page, which association is more linear? One with a correlation of 0.5 or one with a correlation of 0.9? What do you guys think? What's more linear? Yeah, it's a trick question. Remember, I keep kind of emphasizing that correlation does not address form. The value of R does not tell you if it's in a line or a curved pattern. So let me show you what I mean. You actually can't determine the form from R. So here, let's draw like R, it's linear, but it's kind of right in the middle. So let's illustrate that 0.5. It's positive. It's just kind of in the middle of weak and strong. That's linear. Oops. But again, you could have a really strong correlation. This is positive, very strong. R is 0.9, but this is clearly nonlinear. So don't fall into that trap. It's a very common mistake, and that's why I keep emphasizing it for you, because I know students struggle with that concept. R does not tell you if it's linear or curved. It will just tell you the direction and the strength. Okay? Okay, last page of your notes. Now I told you a second ago that the closer R is to 0, the weaker it is, but there is an exception to the rule, as most cases in math. Not necessarily here, and I'll illustrate it for you. This is a kind of a rare instance, but you might see this is different than the curves I've been drawing, and here's why. Go ahead and draw the scatter plot in kind of this U shape. The other curves that I've been drawing, like this one, as x increases, y increases. This one was as x increases, y increases. But here, both things are happening. So I've got a negative association for this half of the U as x increases, y is decreasing, and then it reaches a point where it reverses that pattern. And so this has no association at all, so R would equal 0, no association. R is equal to 0, but the converse isn't true. And what I mean here is, just because R equals 0 doesn't mean that there's no association. All I'm trying to show you is this kind of rare situation where R being 0 doesn't necessarily mean it's weak. This is actually, the way I drew it, very strong, but R is 0 because there's no direction. It changes from positive to negative in the same graph. Is correlation resistant? In other words, if I were to throw an outlier in there, or a point outside of the overall pattern, would R stay the same or would it change? And R changes with those. So an unusual point in the pattern, I'm going to tell you the difference now between like a leverage point and an outlier, okay? An unusual point within the pattern, an unusual point, and we'll have more on leverage points in an upcoming lesson so you can see what they are. Within the overall pattern, strengthens the association. And that makes R closer to that positive or negative 1. And that's called a leverage point. That's if you see a point that might be way off in the distance from the other ones, but it still falls within the same pattern. It's going to strengthen that relationship. And an unusual point outside the pattern, and unusual point outside the overall pattern weakens the association. So R gets closer to 0 in that case, and those are outliers. And those will be easy for you to spot. There is a fancy formula for how to calculate R by hand. You will not have to do that. I will show you how to do that in the calculator. But there are some additional facts I want you to know about R. There's 4 of them, and then we're done with the notes. R requires both variables to be quantitative. I saw another AP teacher post a question the other day. It was from a previous AP exam, and it had a multiple choice question about R, and it said, which of these answer choices would show a correlation of, I don't know, 0.99? And the answer choices would compare, like, let me think really quickly. There was something about a football player's height and their favorite subject in school. Well, one of those is categorical and one of those is quantitative, so that answer choice was out, because you can't have an R value unless both variables are numerical. Okay, so just know that. R makes no distinction between explanatory and response variables. In other words, R will not tell you, just in and of its own, will not tell you what's the explanatory and what's the response variable. R doesn't change when we change units of measure. I could convert everything from centimeters to inches in my data, and the R value, the strength and direction of that association between the explanatory and response would stay the exact same. And lastly, R doesn't have units. You won't ever say R is 0.99 pounds or R is negative 0.3 inches. R doesn't have units. You'll just call it the correlation R, and you'll put equals in the numeric value.